In this circuit diagram, we're asked to compute the power associated with the sources, whether generated or consumed by these sources. And I will use node voltage analysis and show you how we can use it to analyze this circuit. So the first step, as usual, is to identify the essential nodes. And then in this particular case, they have been identified. So this is an essential node, this is an essential node, this is an essential node, that's another essential node. So the ones at the bottom now are different because I have this 2 ohms in here. Okay, so what I need to do is I need to essentially say, well, I have number of essential nodes, just simply 4. That means I need to write 4 minus 1 equations, or KCL equations. So the number of KCL equations, or the number of node voltage equations that I need to write, are 3. So what I need to do is I need to identify one of them as a reference and then write node voltage equations for the others. And in this particular case, it seems to be that any of them be reference is pretty much similar. What I will do is I'll probably avoid these to be the reference because I already know the 28 amps, so maybe I won't choose these as my reference. But the choice of the reference node between this point and this point is pretty much the same, at least in my opinion. So I'll assume that this is actually the reference point or the ground, and then I write my equations as the following. So I'm going to assume that this here is V1, this one here is V2, and this one is V3. Just remember, this V2 in here is actually the voltage difference between here and here, regardless of what's happening in here. So that's if I actually put a probe in here and another probe in here with an ohm meter or an ammeter, I should be able to read that particular voltage in here. So I need 3 equations in order to do this. So let me just write these equations in here. So at node point, or at essential node 1, so the KCL equation tells me, well, it is simply V1 minus 40. This is actually the one going through the 3 ohm, okay, divided by 3. And then we have another one going through the 40 ohms, and that will be actually this here. Let me just make sure that I corrected because I forgot the 1 ohm. So this one here is a 1 ohm and this one here is a 3 ohm. Well, as it turns out, that you can't just say it's V1 divided by 40 because the current is actually going through the 3 amp and the 1 amp in here. Okay, so we need to deal with this 1 and 3 amp. And that's actually straightforward and simple. So the way we do that is, well, this one is in series with this one, is in series with this one. That means these 2 resistors, the 3 and 1, are in series, even though they don't appear that way, but they are in series because the current going through the 3 ohm is the same as the current going through the source is the same going through that. So they are in series. So I could have redrawn that circuit and just basically combine the one in here. But what I will do is I'll just say, well, I'll just add them in here. That's basically, this here is the equivalent between the 3 and the 1 is just simply 4, but I'll just write it in here so that you can see it and remember it. All right, so that's for this current in here. So this current is actually affected by the 3 and the 1. Even though the 1 is after the source, you can just simply combine them because it's a current source. We're dealing with Ohm's law here. All right, so then next what? We do that in here. That's simply V1 divided by 40. And then we have this particular current in here. And that will be plus V1 minus V2 divided by 2. And that should be 0. So that's the first KVL equation. We can just clean it up a little bit, and I believe we'll end up with 31 V1 plus negative 20 V2 plus I believe there's no V3, but I'll just write 0 V3 equals 400. Okay, I'll write these because I'm thinking ahead in terms of Kramer's method if I want to just use these into a matrix. Okay, and I'll just highlight this as this is one of the equations in here. All right, so what do we do next? Well, next we go to V2, which is right here, and we write the equation for it. So the equation for that V2 is just simply, okay, V2 minus V1 divided by 2. That's actually this current in here. And then we go to the other current, which is the one here. Okay, that's plus V2 divided by 4. And the last current in here, I know what that is. It's simply negative 228 equals 0. We'll clean up this equation a little bit, and we'll end up with the following. We'll end up with negative V1 plus 3V2 minus V3 equal 0. Let me just make sure that I've done, well, I think I missed this one here. So this is V2, not V2 divided by 4. So let me just make sure that I highlight this one here. This should be V2 minus V3. There's no difference between what I have done between V2 and V1 and what I'm doing between V2 and V3. It's just because my habit usually I look at this as my reference. It is not the reference. So V3 appears in this equation. So let me just double check. We have V2 minus V1 divided by 2. That's good. Well, V2 not negative V3 divided by 4, that's also good, and we have the negative 28. So if we clean these here, I believe this also shouldn't equal 0. This should be equal to 112 once it's cleaned. Okay, so we do that in here. So that's the second equation that we have. All right. So the third equation, actually at the third node, which is this one here, which is V3. Okay, so I'll write it in here. Okay, so at 3, the KCL is the following. I know the first current. It's actually just simply 28 because it's leaving. And the second current is the opposite of the one I made a mistake on a few seconds ago. This is here V3 minus V2 divided by 4. Okay, so that's V3 minus V2 divided by 4. And then the last current in here is just simply V3 minus, well, this is the 0. So in this particular case, I just have to say V3 divided by 2, and that should be equal to 0. We'll clean it up a little bit, and we'll get to the third equation. And that third equation should be, well, I don't have a V1, so that will be 0 V1 minus V2 plus 3V3 equals negative 112. Okay, and that's basically the third equation. So now what I have is 3 equations, 3 unknowns. All I have to do is just figure out what the V1 is, and what the V2 is, and what the V3 is using a calculator or Kramer's method, whichever you prefer. And you'll end up with the following. You'll end up with this is 60 volts, and you'll end up with this one to be 73 volts, and this will be negative 13 volts. Okay, well, we'll go back in here. Are we done? Well, technically we're done because we can figure out everything we want about the circuit, but what we're asked to do is to figure out the power consumed or generated by the sources. Okay, so what we need to do is we need to analyze the circuit accordingly. So I copied the circuit in here so that so I don't have to scroll up and down, and here. So what I need first is let's figure out the power consumed or generated by this particular source. Well, what we need to do is we need to figure out some sort of a current. So this current in here, I'm going to assume that the current is going that way in here, and I'm going to call it let's say I1, for example, or I40 volts, whatever you want to call it. Let's call it I40. So, well, we know that I40 is just simply the voltage, well, the I40 is the same I40 that is going through this particular resistor, okay, through this particular resistor. They're the same. And of course, it is also the same would be through a resistor that has the 1 and the 3. So that should be easily computed as 40 minus V1 divided by 3 plus 1, or the 4, okay, 3 plus 1. Okay, so let me just repeat. So this I40 is the same as this, the same as that. So what I can do is I can combine the 1 and the 3 together in here. That will be the 4. And then if I want the current going through that, it's just simply whatever voltage I have, which is 40 compared to the reference, minus V1, okay, divided by 3 plus 1, which I know what V1 is. 40 minus 60 divided by 4 is just simply negative 5, and the units are in ohms, so this must be in amps. Okay, all right, so that's negative 5 amps, which means my assumption that the I4 is going that way is wrong, but anyway, we'll keep it that way. Now if I want to compute the power associated with that 40 volts, so what I need to do is I need to do the following. Well, the current now is hitting the negative, so according to passive sign convention, I have to put negative in here. And then what we need to do is we need to multiply, well, I times V. Okay, I is just simply I40, which we know that it's negative 5, times V, which we know it's 40 volts. So that simply is 5 times 40, which is 200 watts. So as it turns out that this particular source is actually consuming power, it's not generating power. That means this source is probably the one that is, well, not probably, for sure, because everything else is consuming power. So that means this source is the one that is generating power. So let's figure out what power is being generated by the 20. So what we need to do is we need to figure out the voltage across it between here and here. Okay, and I'm going to call it V28 volts. Okay, and V28 is simply V2 minus V3. Okay, because that is here. This point in here is just simply the V2. And this point in here is simply the V3. So the voltage across it is V2 minus V3 if I assume that this to be positive. If I assume this to be positive, this will be negative. That would have been V3 minus V2. But that's what I have assumed. So V2 minus V3 is simply 73 minus 13. And that will be, I believe that will be 86 volts. So as it turns out that this, my assumption in here is correct, and this voltage is higher than this voltage. Okay, which sort of makes sense because this is higher than this voltage and this is lower than this voltage. So in totality, this is higher, and it's specifically 86 volt higher. Okay, now we can compute the power for the 28 amps, and that's simply the following. So we have the current now hitting the negative first, so it's negative based on this passive sign convention, and the current going through it is 28 times the voltage, which is 86, and that basically is 2408 watts. So there's about 2.4 kilowatts or so. Okay, so to be exact, 2.408 kilowatts, and that's basically in the negative as well. Like, I forgot the negative in here. So the negative here tells me that this source is generating power, which I already know because this one is consuming power.